Let's review some of the rational functions that we studied back in 11U. So first, for this expression, we want to simplify and state all of the restrictions. So remember, to simplify means that we need to factor, and then we can cancel any common terms in both the numerator and denominator. So we're going to factor the difference of squares in the numerator, and then we have t minus 4, t plus 3 in the denominator. Okay, so we factored numerator, denominator separately, and now what we can do is we see that we have our t minus 4 common, so we can divide both the numerator and denominator by t minus 4. It's gone. So we're left with our final simplified expression, t plus 4 divided by t plus 3. And remember, at this point, you cannot take these t values and cross them out to get the final answer of 4 over 3. Okay, because you're following BEDMAS. BEDMAS says you have to add t with 4, and then you can divide by t plus 3. Okay, so you can't cancel these t's like so. So this is your final simplified answer. But we do need to state restrictions. And those two restrictions are going to be t cannot equal 4 or negative 3. Okay, the 4 comes from t minus 4 cannot equal 0. And the negative 3 comes from t plus 3 cannot equal 0. So basically we can't divide by 0, because then that would give us an undefined expression. Okay, so this is what we did back in 11U. So let's go on to the next problem. So again, we're going to need to factor first. So this is a complex trinomial. You're going to have to use your cross multiplication method. So 2m squared breaks down into 2m and m, and then the negative 3 will break down into 3 and 1. And I need to arrange them somehow with a plus in one bracket, minus in the other, so that my middle term will add up to 1m. So that means I should put the minus here and the plus here. So that will give me 2m squared minus 2m plus 3m, which becomes plus m, and then minus 3. Do the same thing in the denominator. So I'm going to have 3m and m, like so. I need two numbers that will multiply to negative 5, and then afterwards I can cross multiply and add to 2m. So that means I should put the 1 here and the 5 here, and because the 2m is positive, then I'm going to put plus 5 here, minus 1 here. So again, just double check, 3m squared minus 3m plus 5m is positive 2m minus 5. Okay, and again, I am able to cancel out the common term of m minus 1. And then I can write down my final answer, 2m plus 3 over 3m plus 5. Again, you cannot do something like crossing out these m's, or you can't cancel this 3 with that 3. Okay, the entire binomial has to be the same in order for you to cancel anything. So this would be your final answer. Okay. But for the restrictions, we need to make sure that our denominator never equals 0. And I forgot to mention this in the previous example. It's the denominator of the original expression. So that's why we need to look at both of these binomials that exist in the original expression. Even though we canceled out the m minus 1, the restriction is still there. So that means m cannot equal negative 5 over 3 or positive 1. So negative 5 over 3 comes from the 3m plus 5, and then the m minus 1, that turns into m cannot equal 1. Okay, let's move on to the next examples here. So now that we have an additional operation, we just have to, we're going to essentially follow the same steps, but we need to throw in the additional operation of multiplication for this example. So we have x plus 3, x minus 1, divided by x plus 2, x plus 4. Then we're going to multiply this by x plus 2, x minus 2, divide everything by x plus 3, x minus 2. Okay, and now we can start canceling some common terms. I see this x minus 2 here and here, so that's gone. And I can also cancel across this multiplication operation. So that means that I can cancel this x plus 2 with that x plus 2. And then I can also cancel x plus 3 with this x plus 3. So that means that my final answer, most simplified form, is going to be x plus 1 over x plus 4. And now the only thing that's left is for me to state my restrictions. So x cannot equal, I have to look at 4 spots right now. Look at here, denominator, 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 denominator. So based on all of that, I can say x cannot equal positive or negative 2, can't equal negative 4, and it can't equal negative 3. Okay. So the plus and minus 2 come from the x plus 2, x minus 2 terms. Okay. This negative 4 will come from this x plus 4 there. Okay. And then the cannot equal negative 3 comes from the x plus 3 term. So now let's move on to this example. Because we have division, we are actually going to change this into multiplication. So I'm going to combine my 2 steps. I am going to factor, and then I'm also going to rewrite using multiplication. Okay, so for this 2a squared minus a minus 1, I'm going to have 2a, a in the first spot of each bracket, and obviously I can only have a 1 and a 1 in the second spot of each bracket. I need the terms to multiply and then add to negative a, so I should put the negative here and the positive here. Okay. 3a, a, I need a 2 and a 1. One has to be positive, one negative. They have to cross multiply to add to positive a. So that means I'm going to put the 2 here and the 1 here. I'm going to put the plus on the 1, so that gives me positive 3a, and then the minus on the 2 to give me minus 2a. Okay. And now I need to take my denominator of 3a squared minus 11a plus 6, and I'm going to write it in factored form in the numerator now. Okay, so instead of dividing, I'm going to multiply by the reciprocal. So I have 3a. I need my factors to multiply to 6, and then I need to somehow add up to negative 11. And then keeping in mind that this is positive 6, while this is negative 11, means that both of these numbers have to be negatives themselves. So that means I should put down negative 3, negative 2. That'll give me negative 9a minus 2a, negative 11a. Okay. And my last one here, oh, sorry, let me just highlight again. So this used to be my denominator, but now it's my numerator. Okay, so let's just finish off this factoring here. We have now in the denominator, we're going to have 2a, okay. We have negative 2 for the product, negative 3a for the sum, so we're going to have to put a negative 2 here and a plus 1 here. So then that'll give me negative 4a plus a, which is the negative 3a that we need. So again, this used to be the numerator of the divisor. Okay, so that's now over here. Okay, then we change division to multiplication by the reciprocal. So in our next step, we should be able to cancel out some common terms. So let's see what we can do. We can cancel out 3a minus 2, 3a minus 2, that's gone. We can also cross out 2a plus 1, 2a plus 1, and there's nothing else to cancel. So we are going to now write everything as one rational. So in the numerator, I should combine a minus 1 times a minus 3, and in my denominator, I'm going to have a plus 1 times a minus 2. And the last thing that we need to do is, again, state restrictions. So I'm going to have to look at 3 different spots this time. Here, the denominator of my original function, or rational expression rather, and then I have to look here and here. So when it's a division question, I need to look at both the numerator and denominator of my divisor. Make sure that neither of them can equal 0. So that means that a cannot equal 2/3, -1, -1/2, 2, and 3. Okay? So this here is where I got these two restrictions here. Okay? And then the green is where I got the -1/2 and the 2. And then the 3 is, I got that from the numerator here of my second rational, okay? Because it used to be the denominator of the original expression, okay? And then this 2/3 here is already included here. Okay, so now in the next example, we are going to add and subtract our rational expressions. So whenever we do that, whenever we have addition or subtraction, we need to come up with the lowest common denominator first, okay? So when you take a look at these expressions, we notice that our first rational has a denominator of 1. So this is really 2/1 right now. Our second rational has a denominator of n plus 2, and the third one has a denominator of n. So the n plus 2 and the n have nothing in common. Okay, they are completely separate terms. So in order to get our lowest common denominator, that means we are going to multiply them together. So our LCD is n plus 2 times n. So this means that we are going to have to rewrite each of these rational expressions with our new common denominator of n plus 2n. So if that is the case, then I'm going to look at what's missing. Okay. So I'm going to write n plus 2n here. Here I'm going to write n plus 2n. Okay, here I'm going to write n plus 2n. Okay, so whatever is missing from my original denominator, I need to multiply the numerator and denominator both by that missing factor to create my, or rewrite my expression using the LCD. So that means that this 2 here has a denominator of 1. So to change the 1 into n plus 2n, I had to multiply by n plus 2n. So I'm going to have to do the same thing with that 2 in the numerator. So I'm going to write 2 n plus 2 n. And then for the next expression, it used to be 3n over n plus 2. So what's missing is my n. So I'm going to multiply both numerator and denominator by n. And then for my last expression, it used to be 4 over n. So it's missing the n plus 2. So I'm multiplying both numerator and denominator by n plus 2. Okay. So once I've rewritten my expression using my LCD, I can just expand my numerator and rewrite everything. So I'm going to end up with I'm going to have 2n squared plus 4n plus 3n squared. Now this part gets a little bit tricky. You have to be really careful, okay? You need to take that negative right here and you need to distribute, okay? Distribute to both of these terms along with the 4. So that means that I'm going to have minus 4n minus 8 in the numerator. Okay, always very tricky with subtracting rationals, so be careful there. And then my common LCD, my common denominator, is n times n plus 2. So once I have this expression, I can just collect my like terms. I have 5n squared minus 8 over n plus 2. You don't need to expand the denominator, just leave it alone as is, okay? And the next thing is just to state your restrictions. N cannot equal 0 or -2. Now let's look at this next example. When you have this one here, the first thing you want to do is factor. Okay, so let's common factor x from the first denominator. So we're going to end up with x plus 1. Oops, sorry, let me just rewrite that a little bit better. X times x plus 1. Then over here, we're going to have our x over x plus 1 times x minus 1, like so. So this is going to end up giving me, now I need to come up with my lowest common denominator. So let's see here. We have already an x plus 1 in both. So I just need to write that down once. We have an x in the first denominator, and we have an x minus 1 in the second denominator. Okay, so don't write x plus 1 squared. You only need one x plus 1, because that x plus 1 factor is already in both denominators. Okay, so I'm just going to copy down my original rational expressions, just leave a little bit of space to add in my new denominator factor afterwards. Okay. Or you can do it all in the same color, up to you. I'm just using different colors to try to highlight what I'm trying to do. So here, in my first rational, I am missing the x minus 1. So that means I'm going to multiply both numerator and denominator by x minus 1. And then in my second rational, I am missing an x. So I multiply both numerator and denominator by x. So now we can see that both denominators are composed of x, x plus 1, x minus 1, which is my LCD. So let's just expand the numerator, and then we can collect any like terms, simplify as needed. For the denominator, again, don't expand it, just leave it in factored form, like so. This is going to give us x squared plus 2x minus 2 over x, x plus 1, x minus 1. And our restrictions are going to be x cannot equal 0 or positive and negative 1. All right, so now we're going to review how to graph transformations of the function f of x equals 1 over x. So first of all, let's take a look at this table of values to remind ourselves how we get the base graph points. So remember that this function is called the reciprocal or rational function. Okay, reciprocal might be a better way to describe it, because that's how we remember the base graph points. When x is negative 2, the reciprocal value is negative 1 over 2. When x is negative 1, the reciprocal is negative 1. When x is negative 1 over 2, the reciprocal of negative half is negative 2. And then when x is 0, we have 1 over 0, which ends up becoming undefined. Okay, so the reciprocal of 0 is undefined. And then for the positive arm, reciprocal of half is 2, reciprocal of 1 is 1, reciprocal of 2 is half. Okay, so let's take that over here to our graph. So we have 1, 1, half, 2, 2, half, and we have our graph arm like so. Negative 1, negative 1, negative half, negative 2, negative 2, negative half. Then we have our graph arm like so. Okay. And then we need to remember that this graph has asymptotes. So for our asymptotes, we could look at our domain and our range. So our domain is x is any real number except it cannot equal 0, because we had the reciprocal of 0 is undefined. Okay, and then for our range, it's y is any real number, but y cannot equal 0. Okay, and the reason why is because, again, the reciprocal of 0 would be undefined. There's no such thing as an x value that is undefined. Okay, so you can't do the reciprocal of undefined to get y equals 0 either. So that's our range, and based on this we can plot down or show that our vertical asymptote will be x equals 0, and our horizontal asymptote will be y equals 0. So here I go. Remember, the horizontal line is the one that has a fixed y value. So this is y equals 0 going across the x-axis. And then the vertical line is the one that has the fixed x value. So it's going to be the one that has the equation x equals 0 on the y-axis. Okay. So if you remember, back in grade 11, we learned about the difference between 3 types of functions. They were continuous, discontinuous, and discrete. Okay. F of x is an example of what we call a discontinuous function right here. Discontinuous, because it has some kind of break in the middle of the graph. So now we're going to get into more specifics in this unit. So if you take a look, we have 3 types of discontinuities. The first one is called an infinite discontinuity. That's when we have a vertical asymptote in our graph. Okay. So when we have a vertical asymptote, we have a discontinuous function, but more specifically, it has an infinite discontinuity. Okay. When there is a point discontinuity, that means that there is a hole in the graph. And just to show you a very, very tiny and quick diagram on the side, basically, we're going to go over functions in this unit that basically have this kind of break in the middle of the graph, but in the form of this hole here. Okay. So we'll go over those in more detail later on in the unit. And then the last type is the jump discontinuity. That's when the graph is in 2 disconnected pieces. And basically an example of that would be like so. Okay, this would be an example of a jump discontinuity in the graph of a discontinuous function. Okay, so based off of the definitions of the 3 types of discontinuities, we can conclude that f of x equals 1 over x has an infinite discontinuity because it has a vertical asymptote. Now, if you remember our transformed function notation, we've already gone over this a few times in this course, and we learned about it in 11U. So the general function transformed notation is a f of k x minus d and then plus c. So that means when we have our specific function f of x equals 1 over x, then that means that we're going to end up getting our y equals, or you can write g of x equals if you prefer, a over k bracket x minus d plus c. This is bothering me a little bit, so I'm just going to rewrite the y equals, sorry. Okay. So this a value, as always, will represent our vertical stretches, compressions, reflections on the x-axis, and I guess that's it. K will represent our reflections on the y-axis, and then our horizontal stretches and compressions by a factor of 1 over k. Don't forget 1 over k. Horizontal translations represented by d, and then vertical translations represented by c. Okay, so then because we are now transforming with a, k, d, and c parameters, our domain and range is not going to be x cannot equal 0, y cannot equal 0 anymore. And instead, our domain and range will be x is any real number, but not d. D because that's where we translate the graph left or right, which means that we also move our vertical asymptote left or right to the D value. And then our range is going to be y is any real number except C, because C is our vertical translation up and down, which means our horizontal asymptote should also move up or down. So let's practice graphing our transformed functions. And we're also going to state domain and range. So here we have our a equaling -2, and our d value is equal to 3. So that means our function has been vertically stretched by a factor of 2, reflected on the x-axis, and translated 3 units to the right. Okay. So the method that I'm going to show is the step pattern for this first one. So the step pattern method goes like so. You want to move your asymptotes to wherever your translated values are, first of all. So because we have a translation 3 units to the right, that means our x-axis, or sorry, our vertical asymptote rather, is at x equals 3. Our horizontal asymptote does not move because we don't have any vertical translations. So that means our horizontal asymptote has stayed at y equals 0. Okay, so what I'm going to do is I'm going to just show you what the original base graph points were. They used to be with respect to the x and y axes where the asymptotes intersected. They used to be here, 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 like so. And then here, here, and here, like so. Okay? But now that we have both a vertical stretch by a factor of 2 and a reflection on the x-axis, what's going to end up happening is, for example, this point right here, instead of being half a unit away and 2 units up, it's now going to be half a unit away and 2 units down. So that's actually going to be my new point here, using my step pattern method. The next point used to be 1 unit up away from the horizontal asymptote, but now it's going to be 2 units down below the horizontal asymptote. Okay, and then this last point here, it used to be half a unit above the horizontal asymptote. Now it's going to be 1 unit below the horizontal asymptote. So now it ends up looking like so. And I'm just going to delete this arm of the graph so that we don't get ourselves confused. That's just the base function. Okay. And then I'm going to do the same thing with the opposite arm as well. So this point that used to be 2 below is now going to be 4 above the horizontal asymptote. So right there. This point that used to be 1 below the horizontal asymptote is now going to be 2 above the horizontal asymptote. Let me try that again, 2 above. And then this last point here that is half a unit below the horizontal asymptote is now going to be 1 unit above the horizontal asymptote. And, oops, let me just try that again. That's a little bit better. And there is my final graph arm. And I'm just going to delete this one to avoid confusion. Okay. So this is the step pattern method that I just showed for this graph. Okay, sometimes it's a little bit faster to use this method rather than mapping notation or multiple graphs. Okay, but I will show mapping notation in one of the following examples. So in the next example, we have our function horizontally stretched by a factor of 3. So let me write this out. This is going to be 1 over 1/3 bracket x plus, so now we're factoring out this 1/3 coefficient. Remember that when you do 1 divided by a third, it's the same thing as 1 times 3. So that means we're going to be left with x plus 3 in the brackets, and then minus 2. And we have to do this because our function notation is written with the b value completely factored out. So if you don't factor out this b value, then you're always going to get your horizontal translation wrong. Okay, and you can always double check by plugging in one of your final graph points, the x value, into your function and make sure that you get the correct y value back. Okay. So basically what this tells us is that our function has been transformed so that it is now horizontally stretched by a factor of 3, translated 3 units to the left and 2 units down. Okay, so what we're going to do with this information is we're going to practice mapping notation this time. So what we're going to do is I'm going to write down our formula and our points, base points off to the right here. So we have x, y goes or becomes 1 over bx plus d, ay plus c. So that is our general mapping notation formula. We've already gone over this a few times, but always good to write it down again. So given this, we can write that this is going to be x, y will become 1 over a third, which is 3x. Makes sense because this is a horizontal stretch by a factor of 3, so our x coordinate should be multiplied by 3. And then because our d value is -3, we're going to write -3 in the formula, as in we translate 3 units to the left. For ay plus c, we don't have a vertical stretch or compression factor, so a is just 1, and then the c is -2, so we're going to write y minus 2 to show that our graph is translated 2 units down. And then in terms of the base graph points, you're going to have to use the same ones that we used in the table to graph our original 1 over x function. So those would be -2, -0.5, -1, -1, -0.5, -2, -0.5, -2, and then we have 0.5, 2, 1, 1, 2, 0.5. So, excuse me, all of these x coordinates are multiplied by 3, and then we subtract 3. So we have -6 minus 3, -9, -3 minus 3, -6, -1.5 minus 3, so that's going to give us -4.5. Okay, 1.5 minus 3, so that's going to give us -1.5. And then we have 3 minus 3, which is 0. And then we have 6 minus 3, which is 3. And then for all of our y coordinates, we are subtracting 2. So -0.5 minus 2 gives us -2.5. -1 minus 2 will give us -3. -2 minus 2 will give us -4. 2 minus 2 will give us 0. 1 minus 2 is -1. 0.5 minus 2 is -1.5. Okay. So the nice thing about this mapping notation, it's a little bit more work, but you actually have your final coordinates right away. So now we can just plot those down. So we have -9 and -2.5 there. -6, -3, and then -4.5, -4, and I can draw my curve through those points like so. Okay. And then I have -1.5, 0. I have 0, -1, and then I have 3 and -1.5. And I can again draw my points like so in my graph. And then in terms of my horizontal and vertical asymptotes, my vertical asymptote comes from the c value, so y equals -2, going across like so. Make sure you always show and label your asymptotes. And then the vertical asymptote will be -3, that comes from the d value. So x equals -3 right there. And that was the mapping notation method. Okay, for the last example on this page, I'm just going to show you the step pattern method again. So before I go into that though, I need to always remember to write this function out in factored form. So that means that I need to factor out the negative half from my denominator. So I'm going to have negative half bracket x, okay, 2 divided by negative half, same thing as 2 times negative 2. So this is going to be x minus 4. And then I have the plus 5 on the outside there. Okay. By the way, right now our b value here is the negative half, but if you wanted to, you could write that as the a value of negative 2, because the 1 over negative half would give you negative 2 in the numerator. Okay, so whether you say b is negative half or a is negative 2 is actually the same transformation when it comes to rationals. Okay, we'll just keep it the way it is for now. So now let's identify our d and c values, because that's where we're going to put down our vertical and horizontal asymptotes first. So we have our horizontal asymptote going across y equals 5, and our vertical asymptote going down x equals 4. So horizontal asymptote, y equals 5, like so. And vertical asymptote, x equals 4, like so. Okay. So then the next thing we're going to do is I'm just going to, for the sake of having some reference points, I'm going to put down my original base graph points as if this is my y-axis and this is my x-axis. Okay, so these would be the location of my base graph points. Okay, now what I'm going to do is I'm going to take these points and I'm going to reflect them on either axis, doesn't matter, okay, x or y, and I'm also going to horizontally stretch by a factor of 2. Okay, so I'm going to keep this b value as is, and I'm going to say that this is a reflection on the y-axis and also a horizontal scaling by a factor of 2. Okay. So in order to show that here, I'm going to take each of these points on my upper arm, and I'm going to reflect them on the y-axis so that they now come over here. And at the same time, I'm going to pull them away from the vertical asymptote by a factor of 2. So the first point at half 2 is now going to become negative 1, 2. So then for my next point that used to be at 1, 1 is now going to be at negative 2, 1, right over here. Okay. And then my last point that used to be at 2.5 up is now going to be at negative 4.5 up right there. So that will give me the graph arm that used to be on the top right quadrant. Okay, kind of like quadrant 1 position, but now it's kind of like in the quadrant 2 position. Okay, and I'm going to do the same thing with my bottom 3 points here. So this point that used to be here at negative half and 2 is now going to be at positive 1 and negative 2 here. This point that used to be at negative 1, 1 is now going to be at positive 2, negative 1. And then this last point here used to be at negative 2, negative half is now going to be at positive 4, negative half. Sorry, there we go. So that gives me my other arm, and I can just erase my 3 original points. So this is the step pattern method, which I think takes a little bit less time, just because you don't have to show all of the work for mapping notation. Okay, but if you are comfortable and you're faster at using mapping notation, then I would recommend that you just stick with that method. Okay. So now we're just going to practice stating our domain and range for each of these examples. Okay, and basically it's all based off of the your vertical and horizontal asymptotes. So for the number 1 function, our domain is x is any real number except 3, because x equals 3 was our vertical asymptote. For the range, it's y is any real number except 0. For the second function, our domain, x is any real number except -3 for the 3 units to the left. And our range, any real number except -2. Okay. And for our last example, our domain is that x can be any real number except 4. And our range, y is any real number except 5. Okay, so the last thing that we're going to cover is some properties of reciprocals. State the reciprocal of each of the following. So the reciprocal of 5 is going to be 1 over 5. The reciprocal of 1 over 35 will be 35. Actually, let me just write the numbers, the reciprocals, not the equal signs. Sorry about that. The reciprocal of -12 will be -1 over 12. The reciprocal will be 4,000 will be a very small number, 1 over 4,000. And then the reciprocal of -1 over 750 will be a pretty big number, -750. Okay, so some of the properties of reciprocals. If you take the reciprocal of 0, so 0 divided by any number, then that means you would get any number divided by 0, which will be undefined. And then the reciprocal of undefined, well, undefined used to be some other number divided by 0. So when you take the reciprocal of that, now 0 is in the numerator and you're dividing by a non-zero number. So then the reciprocal of undefined will be 0. Okay. If you notice in all of the examples that we did above, the reciprocal of a positive number will always be a positive number. Okay. The reciprocal of 1 is itself 1. If a number is really close to 0 but still positive, like let's say 0.001, or maybe a better way to see the pattern is to write this as a fraction. So we'll write this as 1 over 1,000. Okay, so it's a positive number, but it's pretty close to 0. The reciprocal of that very, very small positive number is going to end up being a very large positive number. Right? Okay. And then the other way around, if the number is a very large positive value, like let's say 10,000, okay, it's a pretty large positive value, then the reciprocal is going to end up being a very small positive number, but still close to, still positive, but closer to 0. And then basically the same results for the negative values. So the reciprocal of a negative number will still be negative. The reciprocal of -1 is itself -1. If the number is very close to 0 but negative, like -1 over 1,000, then the reciprocal will be a very negative number, or a very large negative number, because the reciprocal would be negative 1,000, right? And if the number itself is a very large negative, so for example, if we had negative 10,000, then that means that the reciprocal is going to end up being a very small negative number, as in, and when I say small negative, I mean it's close to 0. Okay, so actually, instead of writing very small negative 1, I just write it's a negative number very close to 0. Okay. So, looking at these properties of reciprocals, maybe it's a little bit hard for us to understand what this means. Let's look at this graphically. Okay. So in order to look at this graphically, we're just going to fill in the bottom half of this page now. So if we examine the graph of f of x equals x and the reciprocal, which would be 1 over x, you might be able to see these properties a little bit more clearly. So if you think about the graph of y equals x, that's just a line with a slope of 1 passing through the origin. So if we have these as our points, point, 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 and we draw our line through these points, okay. So this is my graph of f of x, which is equal to x. Okay. Now, let me draw the graph of my reciprocal. I'm going to do this in red just to make it a little bit, stand out a little bit. So I have my graph of 1 over x, like so. Okay. Okay. And obviously my asymptotes for my rational graph, my 1 over x graph, are y equals 0 and x equals 0. Okay. So now let's take a look at these properties that we discussed above and how we can see them visually with this graphical representation. So if you take a look at the black graph, which is my original function, f of x equals x, the larger the y values of f of x equals x, so the more and more this graph rises up and up to the right, okay, the smaller the y value of g of x. Okay. So once more, there's my black graph, f of x equals x. There's my red graph, g of x equals 1 over x, which is the reciprocal, by the way. So it's the reciprocal 1 over f of x, which is really 1 over x. Okay. So the farther away the black graph arm is from the x-axis, that means that the closer the graph of g of x will be to the x-axis. And then it also works the other way around. If you take a look at the black graph values, closer and closer to 0, okay, so as these y values are getting closer and closer to 0, look what happens to the red graph, okay? The red graph arm is extending farther and farther and farther away from the x-axis. It's actually moving up towards positive infinity, okay? So the smaller the y value on the graph of f of x equals x, that means that the larger the y value of the graph of g of x equals 1 over x. Okay. So let me just write that here. The closer the graph of f of x is to the x-axis, that means the farther away the graph of g of x is from the x-axis. And essentially this means what we saw in at the top of the page. So over here, when we say the number is very close to 0, very close to 0, okay, then that means that the reciprocal is going to get farther away, farther away. Okay. That's what we end up seeing here. Okay. The smaller the y value, meaning closer to 0, that means the farther away the graph of the reciprocal is from the x-axis. Okay. And then here, when we see that the number, the original value, f of x, is a very large positive or very, very negative value, then that means the reciprocal will be very close to 0. Okay, so that just introduces you to some of the properties of reciprocal functions. As we move through the unit, we're going to discuss more and more about the relationship between the original function and the reciprocal function.